this is a topical lecture on the topic of the star formation rate. So let me begin by saying that what I'm about to tell you is a sort of bastard mix between a review I gave last fall and some of my own work. So hopefully it flows semi-coherently, but I haven't had a ton of time to road test this talk because I've been busy with, making sure you all have food and things like that. So please be indulgent. All right, so one of the things that I'm interested in, and that hopefully you are too, is understanding what controls the rate of star formation at large scales. All right, and by large scales, what I mean here is maybe not cosmological scales, although I'll talk about that a little at the end, but galactic scales. All right, what controls the rate at which the gas in the ISM of the Milky Way turns into stars? All right, so one thing that's happened in the last 5 years that's been very exciting is the observations of this have gotten dramatically better. All right, and here's the sort of paradigmatic example. So this is from Leroy et al. 2008. And these are just images of a nearby galaxy in a bunch of tracers. All right, so this is, I just picked this one at random. They've got a sample of order a dozen. All right, so here's a map of this galaxy in H1, the 21 centimeter line. Here's a map in molecular gas as traced by CO. All right, that's just the sum of the two. All right, on the bottom here are tracers of star formation. So we have, all right, here, unobscured star formation is traced by ultraviolet light. Embedded star formation as traced by infrared light. All right, and so there what you're really seeing is dust grains that have been heated up by the gas. All right, and then again, the sum of those two maps. All right, so given this sort of data, you can perform the exercise of asking just a very basic question. How do these things correlate? If I take one of these maps and I overlay it on top of another one, what do I see? All right, so you can just pixelize these maps, and you can then just make a scatter plot of where do things fall. All right, now, if you look at the molecular gas, all right, so here on the x-axis, we've put the molecular gas surface density. And on the y-axis, we've put the star formation rate. And these contours are just showing where the data points fall. So again, what's been done here is you take this map. For every pixel, you read off its column density of star formation, its column density of molecular gas. You put a point in that bin. All right? And what you see is that there is this very strong linear correlation between star formation rate and molecular gas surface density. All right, now, this is a mass per unit time per unit area. This is a mass per unit area. If I divide those two, I get a time scale. All right, and that time scale is called the depletion time. It's the time that would be required to convert all of the molecular gas into stars at the currently observed star formation rate. All right, and that time, as you can see, is about 2 gigayears. All right, so assuming everything stayed the same, it would take 2 gigayears to turn all the molecular gas in a given pixel of a galaxy into stars. All right, now, that's on galactic scales. You can also look on much smaller scales, subgalactic scales, and you can ask about clouds in the solar neighborhood. All right, so here are 2 ways of doing that. All right, so that's the large scale. Now let's look at the small scale, and what I want to spend most of this talk on is trying to put the two together. All right, on the x-axis here is the masses of a bunch of molecular clouds in the solar neighborhood. And on the y-axis is the number of young stellar objects they contain. All right, now this is a reasonable proxy for the star formation rate, and the reason is that the number of young stellar object is defined by a particular evolutionary stage. In this case, the evolutionary stage is how long the disk around the star lasts, such that you pick it out as having an infrared excess in the Spitzer observation. All right, so there's a time scale associated with that. So number of young stellar objects you can think of as defining something like a star formation rate, because, all right, I start creating these young stellar objects. They live for a certain amount of time as YSOs, and then they lose their disks, and they drop out of my YSO catalog. All right, so the number that are in the catalog at any given time is just proportional to the rate at which they're forming, at least as long as they've been forming long enough that I've reached statistical equilibrium between new ones forming and older ones leaving the catalog because they lose their disks. All right, and you see that there's this nice correlation. All right. Here's another way of looking at subgalactic scales and actually galactic scales. And on the x-axis here, this is the luminosity of the HCN 1 to 0 line. All right, so the HCN 1 to 0 line is a tracer of dense molecular gas. And by dense, I mean it traces gas with a characteristic density of about 10 to the 4 to 10 to the 5 particles per cubic centimeter. All right, and the luminosity in that line you can think of as roughly indicating what's just the total mass of gas at that density. All right, and on the y-axis, we've got the infrared luminosity. All right, and again, the infrared luminosity you can think of as being something like a proxy for the star formation rate. All right, and by the exact same argument as YSOs. That is, the infrared luminosity is produced by young, bright, massive stars to the extent that I've reached statistical equilibrium between new stars forming and old ones dying. The total amount of light I have coming out at any given time is just proportional to the total rate at which stars are forming. All right, and again, you see this nice sort of linear correlation. Incidentally, these data points down here are individual blobs of gas within the Milky Way. These data points up here are entire external galaxies. All right, so these are galaxies. These are much smaller pieces within a galaxy, and you'll note this correlation covers like 8 orders of magnitude. All right, now, 8 orders of magnitude hides a multitude of sins, to be clear. You can make anything look like a good correlation if you've got a long enough baseline. Nonetheless, it is striking that you do get this correlation that spans the galactic and the subgalactic scale. All right, so what I want to think about over the course of this talk is, how do we put this together? How do we assemble small-scale star formation, things that are taking place on 1 parsec scales, and get out large-scale star formation averaged over galactic scales? All right, now, there are complications to this picture. All right, so I showed you these nice correlations. Here are some complications. Complication number 1, things seem to depend on metallicity. All right, so this is the same data I showed you before. All right, here I showed you H2 surface density versus star formation rate. All right, now suppose that on the x-axis, instead of putting molecular gas, I just put total gas regardless of what phase it is, atomic or molecular. All right, then I get this. All right, so total gas versus star formation rate. All right, and you see that there's this part that sort of looks like what we saw before. There's this sort of quasi-linear part with a constant time scale. All right, and that's the part of the ISM where it's dominated by molecules. But then there's this turn down where it becomes sharply nonlinear. And what's happening there, if you actually look into it in detail, is that the ISM is switching from dominated by molecules to dominated by atoms. It's switching from H2 dominated to H1 dominated. All right, so what's going on in that steep nonlinear region is that the star formation rate per unit H2 mass is actually staying the same. The H2 depletion time isn't changing. What's changing is the H2 over total ratio, and that's changing nonlinearly in that region. All right, and there's a break at about 10 solar masses per square parsec where you go from H2 dominated to H1 dominated. All right, so that's what you see in nearby sort of solarish metallicity galaxies. Now, you can ask, well, all right, what if I look at a galaxy that's significantly subsolar? All right, and the example of that is the Small Magellanic Cloud. All right, so here is the same sort of analysis done for the Small Magellanic Cloud. The Small Magellanic Cloud has a metallicity of about 20% of solar. All right, here's that same 10 solar masses per square parsec. Again, the pixels are showing you where the data fall. And what you notice is that this nonlinear part is now not below 10 solar masses per square parsec. It's at more like 50 solar masses per square parsec. All right, so we see this same sort of sharp nonlinear turn down, but that nonlinear turn down is taking place at 50 solar masses per square parsec, not 10. All right, so something's different about the Small Magellanic Cloud. The obvious candidate is the metallicity. All right. Here's that phase dependence I talked about before. Star formation correlates with the H2 and not the H1. All right, so again, the same sort of plot where on the x-axis I now have here just the H1, and on the y-axis the star formation rate. And here I've got the H2 in the star formation rate. And what you notice is, again, this is the same plot I showed you before. this really good correlation between H2 and star formation, and this utterly crappy correlation between H1 and star formation. All right, so star formation correlates with the H2, not at all with the H1. And in fact, you see this feature that the H1 surface density hits this wall at 10 solar masses per square parsec. All right, you just don't get surface densities of H1 bigger than that in these solar metallicity galaxies. All right, here is the same sort of data for the Small Magellanic Cloud. All right, and focus on the red and black points, which are basically obtained by averaging. So you can only detect H2 at really high surface densities in the SMC. So you can't quite do that pixel trick. You instead need to average together a bunch of data to get a signal. All right, and that's what these red and black points are doing. And what you notice is that these fall along the exact same linear relation as that data. All right, so that is the depletion time for H2 in the Small Magellanic Cloud is the same as it is in the Milky Way and in every other solar metallicity galaxy. So that is, once you've gotten to molecular gas in the Small Magellanic Cloud, it seems to behave just like molecular gas anywhere else. What's changing is the transition between atomic and molecular gas. That's taking place at a much higher surface density in the Small Magellanic Cloud than it does in the Milky Way or a similar galaxy. All right, so we've got these nice linear correlations, but then we also have all this complexity involved in the phase transitions in the ISM and how that correlates with star formation. All right, so that's the sort of summary of the observational situation. So here are the theoretical challenges. All right, so we've got these large-scale star formation laws, which involve correlations on galactic scales averaging over kiloparsecs. And we've got these small-scale star formation laws that involve these individual clouds, where there are these correlations between number of young stellar objects and the mass of the cloud, between the IR luminosity and the HCN luminosity. Which of these are fundamental? And which is the result? In other words, is star formation really regulated at galactic scales? Or is it regulated at very subgalactic scales? If I want to know what sets the star formation rate in the Milky Way, should I think about that problem as there's some galactic scale process that regulates how quickly I can get gas into stars, or should I think about it as star formation in the Milky Way is a sum of a lot of 1 parsec sized star forming clumps, and the star formation law is simply the sum of the star formation laws in those 1 parsec sized clumps? What's fundamental? What's the results of summing or dividing? And can we unify these different laws and phase dependencies? All right, can we have a theoretical picture that sort of puts all this together? All right, so that's the main theme of this talk. All right, so let's start with the top-down approach. There are sort of 2 ways of getting at this. All right, I see the grad students laughing at this. You got it, Tom? All right. Patrick? See, all right. So I showed this image at this review talk I gave at Yale, and let's just say that there was an extraordinarily sharp age demarcation for who laughed and who just looked confused. The conference was in honor of Richard Larson, who was retiring, and Richard Larson was one of the confused. All right. If you don't know what the hell this is, Google flying spaghetti monster. All right, so the top-down approach. All right, so the top-down approach, the idea is the star formation rate is fundamentally set by galactic scale processes and galactic scale regulation, and it's sort of independent of the local star formation law. All right, that is, what happens on 1 parsec scale sort of doesn't matter. If you're interested in asking, I've got a piece of a galaxy that's, a kiloparsec in size. It's got a certain amount of gas, a certain surface density of gas, say, certain metallicity or whatever else you feel like asking about. How quickly will that turn itself into stars? That's totally independent of what happens on 1 parsec scales. All right, you could change what happens on 1 parsec scales arbitrarily. It wouldn't really affect the star formation rate on large scales. All right, so that's one way of coming at the problem, or one theoretical approach. Yes, question?
I have a question about if you have supernova explosion, inside a 1 parsec scale, that supernova can easily give a breathway to a kiloparsec scale. Maybe impact the star formation on larger scale.
Sure, and supernova regulation would be an example of this sort of large scale. So I mean, everything, ultimately, physics is continuous. It's not like the laws of physics stop operating across some boundary. All right, but for example, so an example would be ultimately what regulates the rate of star formation is the rate at which supernovae are pumping, say, energy or something like that into the ISM. All right. And it doesn't matter what happens on 1 parsec scales, right? Because ultimately, all you care about is how many supernovae you need to hold up the ISM on kiloparsec scales. That would be an example of a model that I would call top-down in this sense, all right? Who cares how quickly 1 parsec scale clouds turn themselves into stars? Ultimately, star formation is going to self-regulate so that you get the right number of supernovae. All right, that's one example of this approach. All right, so here are, in fact, some ways of approaching the problem based on this. So one is the idea that what really matters is the strength of the gravitational instability in a galaxy, the Toomre-Q parameter for the galaxy. All right, and so here are some simulations that were done by Yuxing Li. All right, and what they did is a very nice numerical experiment. They just sort of said, let's take a galaxy and set it up, and we'll have no feedback, no fancy physics, no nothing. We're just going to set up a galaxy, and we're just going to vary the surface density of the gas so as to change the Toomre-Q in the galaxy. All right, so Toomre-Q, hopefully everyone has heard of it. If not, it's simply a measure of the strength of gravitational instability in a disk environment. All right, and the gravitational instability is determined by a competition between gravity, which wants to clump things together, pressure, which wants to push them apart, and shear, which wants to tear them apart. All right, so you can vary Toomre-Q, and what they have plotted here is, as a function of the Toomre-Q they initialize their simulations with, how quickly does star formation proceed? And they address that by assigning it a time scale, which they get simply by running their simulation for some length of time, measuring the rate at which gas collapses into stars, and assigning a time scale based on that. All right, and what they find is there's this very nice correlation between the strength of the gravitational instability and the Toomre-Q parameter they start in their simulations. Well, and there's some observational support for the idea that this might be important. So this is a map of the Large Magellanic Cloud by Yang et al. All right, and the red points are the locations of massive young stellar objects as traced by Spitzer. All right, so that's telling you where the star formation is taking place. All right, the gray scale is just a continuum image. I think maybe it's a 21 centimeter image, I can't remember. But the blue is a map of where they think the gravitationally unstable regions are. All right, so the blue contour is just outlining where in this galaxy would I say that the Toomre-Q is 1 or less. All right, based on the gas surface density, the stellar surface density, the stellar and gas velocity dispersions. All right, so they've got a combined Toomre-Q that includes gas and stars. The blue outline is where the gravitationally unstable regions are, and you see that there's a reasonably good match between that and where the young stellar objects are. All right, now, a skeptic could say, well, all right, that Q equals 1 contour includes almost all of the galaxy. I think that's a fair criticism to make. Nonetheless, it is noticeable that there's a lot of area out here, but no young stars. All right, so that's one example of a sort of top-down approach to the problem. All right, another is a feedback-regulated approach, and this is like your supernova example that you asked about. All right, so here are 2 examples of feedback-regulated star formation models. In this simulation, and Eva Stryker has a model like this, which she talked about at that conference, and I forgot to take that little notation out, sorry. And in fact, it works perfectly, because you will hear from Eva Stryker in 2 weeks, and I am sure she will talk about her model. So, Eva Stryker's model falls into this category. Saved by my own lack of cleverness or something. I outsmarted myself. So here's an example of a simulation like this from Claire Dobbs. Here's an example of a simulation from Phil Hopkins. All right, and in these stories, what's going on in these simulations is you've got gas that starts collapsing down into molecular clouds and star forming and forming stars, and then there's some form of stellar feedback that's inserted. Now, the exact form of that feedback is very much a subgrid model. All right, so in Claire's simulations, there's some recipe for momentum injected by supernovae. In Phil's simulations, there's some very, very complicated recipe that supposedly includes all forms of massive star feedback. All right, but you can see what happens in the simulations. You start getting these dense clumps forming. All right, and as these dense clumps form, they then get blown apart. All right, you can see all these explosions going on. As these dense regions form, they get blown apart by stellar feedback. All right, and exactly what that feedback is depends on whose model you like. But the point is that that feedback is ultimately what limits the rate of star formation in a galaxy. All right. How quickly you can get stuff into stars is determined by, when you put stuff into stars, how effective are they at blowing up the star-forming region. All right, now, a key characteristic of these models is that the small-scale star formation law, what's going on 1 parsec scales, really doesn't matter. And here's some examples of this from Phil's simulations. All right, and this is true of the other simulations too, but it's particularly a good example from Phil's. So what Phil did is he said, well, all right, I have some recipe for gas collapses to some high density that I can't resolve. Then I have some recipe for how efficiently or how quickly I turn that gas into stars. All right, and that's characterized by this epsilon parameter. All right, and the formal definition of this is the gas reaches some maximum resolvable density. All right, at that density I can assign a free fall time. And then I say what fraction of the gas gets turned into stars each free fall time. All right, and Phil varied this from 0.35% to 6%. All right, and then he asked, well, all right, as I vary this, what happens to the star formation rate in the galaxy as I change this parameter, leaving everything else the same? And the answer is absolutely nothing. The star formation rate in the galaxy is totally insensitive to this parameter. Well, how can that be? Well, the physical reason is that ultimately, again, what's regulating star formation, the throttle here, is how quickly gas can collapse and then how effectively it gets blown back up. I need a certain amount of feedback to keep my ISM in a sort of pressure balanced state. And the density distribution will self-adjust in order to give you enough dense gas so that you get that level of feedback. And that's what's illustrated here. So this is the mass distribution in these 3 different simulations with these different values of epsilon. So that is, how much of the mass is at a density of n or less? All right, so you see there's a lot of the mass at a density of 10 to the 0 or less. The amount of gas at high densities is very, very different depending on which value of epsilon you choose. All right, so if you choose a low efficiency, the galaxy responds by putting a lot of mass at high density. If you choose a high efficiency, the galaxy responds by putting only a little bit of mass at high density, in such a way as to keep the total rate of star formation at the equilibrium value. All right, now this is true of Phil's models, it's true of Eve Ostreicher's models too, and as I said, she'll certainly come tell you about that in a couple of weeks. All right, so in all of these models, a key characteristic is what regulates star formation is galactic scale, and the way that regulation happens in practice is that the small scale structure of the galaxy self-adjusts so as to give you the right star formation rate on large scales. All right, so if you need to have more dense gas to make the star formation rate match what the large scale dynamics want, that's what will happen. If you need less dense gas, that's what will happen. All right, so that's the characteristic of a top-down model for the star formation rate. All right, so now this is a very appealing picture, particularly for people who are interested in like cosmology, because it sort of means that, you know, it doesn't matter what you do on small scales. You can do anything, and it'll be okay as long as you got your feedback right. All right, and cosmologists really, really like to hear that, because it makes their lives easy. All right, so these models are very, very popular with the galaxy simulation people. Whether they're right is a separate issue. All right, now, I should say, one serious worry about this is that the results then do depend sensitively on your subgrid feedback model, and that is not at all resolved in these simulations. And here's just an example. All right, so in this simulation, all right, of Phil Hopkins, where he's blowing stuff up, all right, he has some recipe for how much momentum is injected by massive stars, and that is what sets the star formation rate. So I didn't plot it, but if he changes his recipe for momentum feedback, that does change the star formation rate. All right, so you're very sensitive to having gotten that recipe right. All right, and an important note is that in Phil's recipe, in particular, the momentum delivered by the stellar feedback is many times larger than the momentum of the stellar radiation field. All right, so the idea here is that what's happening is that radiation gets bottled up, and radiation pressure is actually what's driving most of this effect. So the idea here is that stars emit photons, those photons get bottled up by the dense gas around them, and they bounce back and forth many times and transfer a lot of momentum to the gas, and that's what's blowing those clouds up. All right, now physically this is certainly possible. This is a problem you probably did at some point in your undergraduate relativity course, right? So I have two mirrors, and I just bounce a photon back and forth between them a very large number of times. What happens? Yeah, well, in a laser this happens. All right, but if I just bounce this mirror back and forth, or this photon back and forth, right, every time the photon bounces, it imparts some momentum to one of the two mirrors. All right, so there's nothing to hold the mirrors in place. They'll start accelerating. All right, now, the consequence of this is that the photon loses some energy. It gets redshifted because, of course, now it's bouncing off a mirror that's moving. So when it comes back off, it's at a somewhat lower frequency. So I take the photon's energy and I use it to put momentum into the two mirrors. All right, so that's essentially what's going on in Phil's model. All right, now what's shown here is a simulation showing that actually probably doesn't work. All right, because the ISM is not a very good mirror. It has all these instabilities in it that make it very hard to bottle up radiation. So if you try and bottle up the radiation, all right, so these are some simulations of mine. What's going on here is that radiation is being injected from the bottom of these boxes, and it's running into interstellar gas. All right, and that interstellar gas is supposed to keep it bottled up and extract energy from the radiation field so that it gets accelerated like you see in Phil's models. All right, and what this is showing here is that that doesn't work very well. All right, instead what happens is you initially start driving the gas upwards, but then there's this instability that sets in and prevents the radiation from getting trapped effectively. All right, this is actually a Rayleigh-Taylor-like instability. It's a radiation Rayleigh-Taylor instability. All right, so
what efficiency do you get?
Basically, you just get a momentum of L over C. All right, for realistic ISM parameters, you can get, so the complicated answer is that there are two dimensionless numbers for this problem. One is the Eddington ratio measured at the dust photosphere, and the other is the optical depth measured using the opacity of the dust photosphere. And there's a formula for what will happen given those two numbers. All right, and we actually, in this paper and its follow-up, we mapped out the full parameter space as a function of those two numbers. But if you put in numbers that are sort of realistic ISM values, you basically find that the efficiency of momentum transfer to the gas is just what you get from the first absorption. You don't get any significant enhancement by bottling up.
So how this curve can be modified?
Instead of these solid lines, which is what Phil puts in, he should be getting these dashed lines. So it's not a small difference. It's a factor of, it's an order of magnitude. Yes?
How do you keep track of the momentum balance? Is like a particle in a cell?
No, this is radiation hydrodynamics, so we haven't heard about that yet. Jim Stone's going to come and talk about it, but you can you can write down, in addition to the ordinary equations of hydrodynamics, you can write down the equations of radiation hydrodynamics. All right, and those equations have terms that involve the momentum and energy content of the radiation field. All right, so in addition to the equation of gas momentum conservation and the equation of gas energy conservation, you also have equations for radiation energy conservation and radiation momentum conservation. And there are coupling terms that allow the radiation and gas to exchange energy and momentum. All right, so these simulations were done with a code called Orion that actually solves the coupled equations of radiation hydrodynamics and keeps track of that. This is two-temperature flux-limited diffusion. All right, but actually the instability has been demonstrated by Zhang et al. Using Jim Stone's new variable Eddington tensor code, and they haven't quantitatively, checked what the momentum transfer rates are yet. I know Shane Davis is working on that, but qualitatively, the instability certainly occurs even with a VET method. Yes.
What is the difference between the three simulations?
Oh, the different, sorry, oh, these 3 simulations? Okay, those are these different dimensionless numbers. So, all right, so I said that there are these 2 dimensionless numbers. One is the optical depth at the top of the dust photosphere, and the other is the Eddington ratio, that is the ratio of radiation to gravitational force at the top of the dust photosphere. So these 3 simulations are, so T is the value of that optical depth. It's, all right, so that's 3, 10, and 10. And F is that Eddington ratio, an Eddington ratio of 0.5, 0.25, and 0.5. All right, so those are some of the, so these are 3 values of those parameters. We also have, which I haven't shown here in a subsequent paper, some runs we did where we took the limit of f goes to infinity. All right, and you can look at what happens as f goes to infinity, and then you can try and map out what happens as a function of f and t. Yes?
How does this actually affect the star formation rate?
So how does it affect the star formation rate? Well, in Phil's models, at least, if you reduced his momentum flux by a factor of 10, his star formation rate would go way up. Now, whether that's right or not is a separate question, but it is certainly the case that if you just take Phil's simulations and you put in this amount of momentum instead of the amount he's actually putting in, his star formation rates would go way up.
Why?
Huh? Sorry. What were you saying?
Why it's way up?
Why way up? Well, again, so in these models, what regulates the star formation rate is that I need to be forming stars fast enough that I can keep the ISM in a marginally stable state. Basically, the ISM starts to collapse. I need to put in enough momentum that I can push it back out. All right, so if I get less momentum per unit star formation, then I need a higher star formation rate to make up for that.
So, yeah, would you get using the feedback?
Yeah.
That seems more reasonable. Would you get essentially the so-called Zuckerman event catastrophe? I mean, would you get star formation rate?
Yes, you would get a star formation rate that would be way too high for the Milky Way. Again, in Phil's models. If you just take Phil's simulations, I mean, so again, I don't have the plot in the talk, but but Phil does in fact have a plot in his talk of star formation rate if you just turn off this radiation pressure effect, and it is indeed much higher and too high for the Milky Way.
How many orders higher?
I mean, depends on exactly how you set up the galaxy. Depends on which. He's got a bunch of different simulations and a bunch of different parameters, so it's not, there isn't a simple answer to that. Depends on other details, but, significantly, not a small amount. Mm-hmm.
Do you think the magnetic field will modify this?
Possibly. It's a good question. I don't know. I mean, we speculate that probably not unless it's so strong as to be, sort of as to render the entire thing magnetically subcritical. But, I certainly would expect a factor of order unity modification. Whether it's an order of magnitude modification, I don't know. There's another instability that can only happen with a magnetic field. So this is a radiation Rayleigh-Taylor instability. All right, there is also the photon bubble instability. And this is not photon bubble instability, because photon bubble instability requires a magnetic field. But if you have a magnetic field, that actually enables another form of instability. So I don't know which way that pushes the, once it goes into full nonlinear development, I don't know if that gives you more or less momentum transfer. But there's in fact another instability that would occur if you could turn on a magnetic field here. All right, and I think Shane Davis is looking at that too, because he's doing this with Athena's VT method, and Athena has MHD.
Actually, in a sense, you have been a bit, here you assume from the initial conditions that
Totally laminar, yeah.
the gas is homogeneous.
Yes.
While I guess in reality, you get this extremely clampy.
That's right.
Which makes the situation even worse.
That's right.
Because you have channels.
No, that's exactly right. There are pre-existing channels. This is the best case for the radiation driving, and it still doesn't work. Yeah. In reality, it's even worse. Although I should say, I mean, this is all done in dimensionless units, but if you put in dimensional scalings, the time for the instability to go nonlinear is very small compared to any reasonable galactic time scale. Okay, any other questions on this? All right, we'll move on. All right, another potential issue with this is it's very hard to see how metallicity would make a difference in this top-down approach, and that's potentially problematic. All right, so again, here are some of Phil's models. All right, and here is, so you might expect metallicity to make so you see that there's this phase dependence, right? That star formation occurs only in H2, and where the H1 to H2 transition occurs depends on the metallicity. All right, but in Phil's models, whether you have molecular chemistry or not has no effect on the star formation rate. All right, here are again 3 different models, one with chemistry, one without, one with cooling, one without. All right, and the star formation rates you get are totally unchanged. And again, this is because ultimately what's controlling the star formation rate is the rate at which you have to blow up the ISM to keep it from collapsing. And so who cares what phase it's in? Its weight is independent of its phase. Yes?
So do the Bolano et al. Results show that the global star formation rate of the SMC depends on the metallicity? I buy that the local star formation rate seems to have metallicity.
Well, when you,
But is it like, if it
right.
didn't, then maybe the structure
Yeah.
of the gas, the SMC, would be different such that you would get the same global star formation rate.
Okay. It is the case, so you are right that the effect on the global star formation rate is less than the effect on the local star formation rate, but even the global star formation rate is modified. All right, and the way you could see that is you could take Bolano et al.'s like SMC map, and you could say, well, suppose that I just magically declared that all the H1 with a column density above 10 solar masses per square parsec was actually H2 and had a depletion time of 2 gigayears. How would that change the depletion time of the galaxy as a whole? And it would go down. All right, it wouldn't go down by, an order of magnitude, but it would go down by a factor of at least a few. All right. Yes.
Right, so I tend to think of the feedback as sort of the energy you need to balance the cooling,
Yes.
right? And if you have metals, the cooling rate jumps off by an order of magnitude, so don't you have?
So the reason that's not what's going on here, all right, is that the cooling rate is not in the dense gas, the choke point in the cooling is not how quickly can I radiate away the energy, it's how quickly can I turn turbulence into kinetic energy. The density is high enough that whether you've got metals or not, or you sort of doesn't matter for the cooling rate, right? The density is high enough that once you turn the kinetic energy into thermal energy, it gets radiated away in a much less than a dynamical time, whether you've got metal cooling or not, all right, in the dense ISM. All right, and so, the rate limiting step in the energy loss is not how quickly can I radiate the thermal energy. The rate limiting step is how quickly can I turn bulk motion into thermal energy, and that's independent of the metallicity.
Very dependent on your subgrid model.
I don't know if that's actually true, right? I mean, it's viscous shock dissipation. It's, this is the nice thing about artificial viscosity, right? The shock jump conditions don't change. All right, and so the consequence of this is that there's no metallicity dependence and no phase dependence in these models. And that doesn't agree with what you see in the SMC. All right, so I think that's the drawback of that approach. The alternative is the sort of bottom-up approach, where you say it's totals all the way down. All right, that really, why is the star formation rate at, 1 kiloparsec what it is? Well, it's because of the star formation law that operates on 100 parsec scales. And that's modified by the star formation law that operates on 1 parsec scales, and all the way down to some smallest scale, which is to be specified. All right, that's the sort of extreme version. The local star formation law is what matters, and the galactic star formation law is simply what is produced by that local star formation law plus whatever it is that controls the galactic scale distribution of where the gas is and what its sort of density structure is. All right, so, one version of this is, and this isn't even so much a model as simply a sort of observer's empirical rule. All right, and I call this the dense gas model. And what I mean by this is, all right, so we saw earlier this correlation between the HCN luminosity and the star formation rate. All right, and it's a very nice linear correlation over many orders of magnitude. All right, and so the idea is, well, maybe what really matters is the amount of gas that's at densities above some threshold or high enough that it can be emitting in, say, HCN. All right, so the star formation rate, therefore, is simply the amount of mass in this dense phase where the definition of dense is to be specified, divided by some time scale associated with this dense phase. All right, so that is, the star formation rate depends on how much mass is there at a density of 10 to the 4, and if I know that, I know everything. All right, and so for example, and so that's, this has been proposed by Heiderman. Charlie Latta proposed something similar. All right, so here's total mass, here's star formation rate. All right, and the open circles are sort of normal galaxies. The filled circles are sort of ULERGs, etc. All right, are sort of for dense gas. And his argument is that basically the difference between a normal galaxy and a ULERG, the difference between the Milky Way and ARP 220, is what fraction of the ISM is at or above this density threshold where star formation turns on. All right, and I know Frédéric Bourneau has proposed similar models. All right, so the idea is that there's this threshold where star formation turns on. What you care about is how much gas is above that threshold. All right, now, this sort of looks observationally like what you see here. So here is from observational work from Amanda Heiderman. On the x-axis is the gas surface density. On the y-axis is the star formation rate. And what they see is that below 100 solar masses per square parsec, all right, you have this sort of nonlinear correlation between gas surface density and star formation rate. It's increasing rapidly. And then once you're above 100 solar masses per square parsec, they argue it sort of, flattens out. Now, you can look at that data and draw your own conclusions about the extent to which you believe there's really a break there, but that's at least the claim. All right, now I'd say the biggest criticism of this model is that there's no sound physical basis for choosing these numbers. It's not clear why a density of 10 to the 5 is special. All right, what's special about 10 to the 5? Why isn't it 10 to the 3 or 10 to the 9? All right, and similarly, because there's no model for why that density is special, there's no model for what that timescale should be. Why is the timescale for star formation at a density of 10 to the 5, whatever it is the observations require? Why isn't it something totally different? All right, so there's not much physics in this model. It's more of a sort of observer's rule of thumb than it is a real physical model. Yes?
It's the same parameters for the Toomey criterion?
Well, but in the Toomey criterion, there's physics there, right? Like there's gravitational instability. I think I understand. Here, it's not like this stuff is Toomey stable and this stuff is Toomey unstable. All right, it's not like I'm switching between Toomey stability and instability here. All right, so there's no sort of physics here, whereas there is physics in the Toomey Q. Does that answer your question? Okay. Yeah. I mean, as far as I know, no one has come up with a good physical model for this. All right, it's simply an observer's sort of correlation. All right, another thing you can do is you can say, well, all right, maybe what matters is in fact something like the local volume density. All right, so here's some work of mine where on the x-axis, I have taken all of these local cloud observations from Charlie Latta and Amanda Heiderman and people like that. And I've said, well, all right, what we can observe is the surface density. Let's just do the dumbest thing imaginable. Let's just say, suppose that the dimension we can't see, the dimension along the plane of the sky, is comparable in size to the 2 dimensions we can see, right? So these are resolved objects. We can measure their areas on the sky. Suppose that we say that, the characteristic size scale is like the characteristic length is just the square root of the area. All right, the characteristic depth in the plane of the sky is that characteristic length scale, and let's assign a density that way. All right, and if we assign a density that way, from a density, there's a very natural time scale you can compute. It's the free fall time scale. All right, and so you can plot surface density divided by free fall time scale, and on the y-axis, you can plot surface density of star formation, and lo and behold, you get this very nice correlation. All right. Now, just like, all right, so the normalization of this correlation defines a dimensionless number, because this is mass per unit area per unit time. This is mass per unit area per unit time. These two things are correlated. All right, they have the same units, so the slope is just a dimensionless number. All right, and that dimensionless number we call epsilon ff, and it turns out to be 0.01. All right, that is, now you can think of this as, on average, at what rate do I put mass into stars per free fall time? That is, in one free fall time, how much of the mass do I put into stars? And the answer is about 1% of it. All right, so 1% of the mass goes into stars every free fall time. All right, and you see something similar in this. All right, so this quantity here is called SFR-FF. So this is looking at HCN. All right, so this is IR luminosity. And on the y-axis is, all right, so from the IR luminosity and the HCN mass, all right, so remember LHCN gives you an HCN mass. And you know what the density of that gas is because you know what the critical density of the HCN molecule is, so you can get a time scale from that. All right, so I know a mass, I know a time scale, I know a star formation rate. I can again define this quantity epsilon FF, or as they've called it SFR-FF, and the data give you of order 1%. Now, there is this trend here. It's not totally clear to me if that trend is real or if it's simply the fact that HCN is not a totally unbiased tracer of mass. All right, nonetheless, you get this value of about 1%. All right, incidentally, this gray band is just a factor of 3 scatter, so you can see how big the scatter is. All right, so the question is, why is that epsilon FF so low? All right, where does that 1% come from? All right, and the basic story here is one that I first worked on as part of my PhD thesis, and it's subsequently been taken up by a number of people, including Patrick, Paduana Nordland, Phil Hopkins, Christoph Fedorov has gone and beat the hell out of this problem. And like by beat the hell out of it, I mean he ran like, 15 or 20 huge simulations to try and figure this out. All right, and I will not give you the gory details. I'll give you the short summary. So the short summary is that this 1% number comes roughly from the properties of turbulence. All right, and here's how you can understand it. All right, suppose that we've got some molecular cloud on big scales. All right, so on big scales, molecular clouds have roughly equal amounts of kinetic and gravitational energy. All right, that is their virial ratio, which is the ratio of kinetic to gravitational potential energy, is about 1. All right, now let's ask how these things scale with length. All right, so let's consider some subregion of size little l. All right, now here's what I know about turbulence. One thing I know about turbulence is that it obeys what's called a line width size relation. That is, the bigger the size scale I look at, the larger the velocity dispersion I will measure. All right, so if I've got a box of a turbulent, so if the air in this room were turbulent, all right, and I just asked, what's the velocity dispersion of the air in this room, I would get some number. If I then took a little cubical box much smaller than the size of the room and I asked, what's the velocity dispersion just considering the gas in this little box, I would get a much smaller number. All right, and the scaling is the velocity dispersion goes like length scale to the 1/2 power. Now let's think about what that implies for the ratio of kinetic and potential energy. All right, so if I pick a random region of size L, its mass is going to go on average like L cubed. All right, now its kinetic energy is going to go like mass times velocity dispersion squared. All right, so that's L cubed times sigma squared, that's L to the 4th power. Its potential energy, on the other hand, well, potential energy goes like mass squared over length. That's L to the 5th power. All right, so if potential and kinetic are equal at the large scale, as I go to smaller scales, the kinetic energy goes down more slowly than the potential energy. Potential energy is going down as the 5th power of length. Potential energy is going down as the 4th power. All right, so the typical region inside this cloud is gravitationally unbound. The only way it will be gravitationally bound is if it's denser than the average. All right, and you can try and say, well, how much denser than the average does it need to be? All right, and if you say then, well, all right, how much the cloud is denser than the average, now I can invoke another fact I know about turbulence, which is that it produces a log normal distribution of densities. All right, I can say, well, how much of the density distribution is above my threshold? All right, and when you do that, you find that a very small fraction of the gas is above the threshold, and that's the basic reason why the star formation rate is low. Now, you can do that at varying levels of sophistication. When I first proposed this idea, we had just a single density threshold. We had a single time scale for collapse of that density threshold, and everything was very simple. That was clearly too simple an idea. It has been elaborated by these people who have come up with considerably more sophisticated models where you can think about different length scales and think about the turbulence on different length scales. But the basic idea is just this kinetic energy argument. It all reduces to this argument more or less. All right, and you always get epsilon FF is much less than unity. You don't always get 1%, but you get much less than 1 for any realistic model. All right, so this is at least a plausible reason why the star formation rate on small scales is low. All right, now, how do we extend this out to galactic scales? If we want to build a bottom-up star formation law where the local one's what is important, how can we do that? Well, all right, in order to do that, I have a recipe now which tells me if I've got gas at a given density, how quickly do I turn it into stars? How do I get a characteristic density from galactic scale information? All right, well, in Milky Way-like galaxies, you observe that GMCs have this roughly constant surface density, about 100 solar masses per square parsec. All right, and they have characteristic masses that are given by the galactic Tumray mass, all right, which is what you expect if they're created by gravitational instability. So if I've got a mass and I've got a surface density, I can solve for volume density. All right, and I get a volume density, and here's how it scales with galactic surface density, GMC surface density, and the velocity dispersion of the ISM squared. All right, and that gives me a density. Now, this will only work in sort of normal galaxies, and the reason it will fail to work is that GMCs have a surface density of 100 solar masses per square parsec. But if you go look at the center of ARP 220, all of ARP 220 is above 100 solar masses per square parsec. Clearly, you do not have isolated giant molecular clouds in ARP 220. All right, so there you can say, well, all right, let me make an alternative estimate for the density. My alternative estimate is there aren't these isolated gravitationally bound molecular clouds. Instead, the entire ISM is just one continuous molecular medium. All right, and I will set the density simply by the condition that the Tumray Q of the galaxy has to be about 1. All right, that the galaxy will self-regulate to a Tumray Q parameter of 1. And that gives me a density, because it turns out one way of writing down the Tumray condition is that Q equals 1 corresponds to when the free fall time is the same as the orbital period, leaving out factors of order unity. All right, that's one way of understanding the Tumray stability condition, is that it's equivalent to saying the free fall time is the same as the orbital time. All right, and that gives you a density, which I've called rho t here, which depends on the galactic rotation period and the Tumray Q. All right, so just as a simple ansatz, you can say, suppose the density in the star-forming clouds in the galaxy is whichever of these two gives me a higher estimate. All right, that is, the gas will either be at the density demanded by Tumray Q equals 1, or the density of isolated molecular clouds that are sort of decoupled from the galactic scale flow. All right, and if you do that, then I can assign a characteristic density to every galaxy. And I can make this same sort of plot, surface density divided by free fall time versus star formation rate. But now, in addition to the local clouds, the red points, I can put entire galaxies on this plot too. All right, so the blue and black symbols here are galaxies both locally and at high redshift. All right, where I have estimated the free fall time by exactly the argument I just wrote down. All right, so it depends on the rotation curve of the galaxy, depends on the surface density of the galaxy. The contours here are the local galaxy observations pixel by pixel. You can do this pixel by pixel, and what you see is that they all fall along this common line of epsilon FF is 1%. All right, so you can build a global star formation law out of a local one. All right, now, there are definitely some cop-outs and limitations in this approach, and I'm going to mention just one briefly because I'm almost out of time. I have 5 minutes left, which is that, all right, that surface density of 100 solar masses per square parsec, well, I put in from observations, but that probably comes from somewhere. And that somewhere probably has something to do with feedback. So really, you can't get a completely top-down or completely bottom-down picture. Reality is certainly somewhere in between. All right, the top-down people need to take their epsilon FF and something like that from observations or their density distributions. I need to take that surface density of molecular clouds from observations. Reality should actually be able to predict all of this stuff, or a good theory should be able to predict all of this stuff. All right, let me talk very briefly for the last 5 minutes about the phase dependence. All right, where does that come from? Well, all right, to answer that, you first have to understand what controls the phase of the ISM in the first place. All right, why is the ISM of the Milky Way mostly filled with H1 and not H2? All right, now, that's actually a deep question because H2 is the lower energy state. All right, if I just have a chamber of atomic hydrogen on Earth, I just get a cylinder of atomic hydrogen, it will very quickly convert itself into molecular hydrogen. That's the lower energy state. Why is that not the dominant state of hydrogen in our galaxy? All right, and the basic reason is that H2 can be dissociated by FUV photons, and stars are very good at producing FUV photons. All right, so If I have an H2 molecule that is sitting by itself in interstellar space, in not very long, by galactic standards, it will be hit by a far ultraviolet photon that will excite it, and then it will be dissociated. So I only get molecule-dominated regions in places where that interstellar FUV flux is attenuated sufficiently strongly. As a result, molecular clouds tend to have a sort of layered structure. They've got outer layers that consist of H1, and where the gas is fairly warm. All right, the carbon actually does something similar. So the carbon is kept in the form of carbon-2. It's ionized. And then as I go into the cloud, the dust attenuates the ultraviolet photons. And as a result, I get a chemical transition from H1 to H2 once I've attenuated the FUV radiation field enough to bring the dissociation rate down. All right, and eventually, further into the cloud, I get a similar attenuation. All right, so carbon chemistry is very similar. Carbon gets CO gets dissociated by FUV photons, so I need to attenuate them, and then I get a transition from the dominant carbon repository being carbon-2 to CO. All right, here are the equations that describe this. All right, so H2 formation balanced against H2 photodissociation. All right, and the equation of radiative transfer describing the FUV radiation field. All right, and here are some similar equations describing what controls the temperature of the gas. Line cooling balanced against the dominant heating source, which is the grain photoelectric effect. That is, I've got dust grains, FUV photons hit the dust grains, knock electrons off them, those electrons bounce around and heat up the gas. All right, and I will not go term by term because I'm out of time. Now, it turns out that with some algebra, you can actually render these equations into something that's quasi-analytically solvable. All right, and the bottom line is that the answer depends on these two dimensionless numbers. One is just what's the dust optical depth of the cloud, that's this tau r. And the second is this dimensionless parameter describing how strong the radiation field is. All right, it looks sort of like an ionization parameter for those who are familiar with such things. It's a photon to baryon ratio. All right, and the way this works qualitatively is that there's a characteristic shielding column that is required before you transition from H1 to H2. All right, you need a certain column of gas to eat up enough FUV photons before you go from being H1 dominated to H2 dominated, and that column turns out to be 10 solar masses per square parsec at solar metallicity. That's why you don't see column densities higher than 10 solar masses per square parsec at solar metallicity. But of course, what's doing the attenuation here is dust. So if I take away 80% of the dust grains, like in the SMC, because I've only got 20% solar metallicity, well, then I need 5 times as much column before I get shielded. All right, and that's what's shown here. All right, so let's focus on the dashed lines. That's the H1 column versus total column. And what you see is that at solar metallicity, that's the black line, all right, H1 column equals total column until 10 solar masses per square parsec, then H1 stops going up. But if I go to 1/10 solar metallicity, that's the green line, that transition moves to 50 solar masses per square parsec, just like, or 100 solar masses per square parsec. Now I've left out some details, but that's the basic picture of what's going on. So I will end on this slide since I'm out of time. So why does star formation only occur in the H2? Why is it correlated with the H2 and not the H1? All right, well this is actually very subtle. You might think that it's because H2 is important for cooling. That would be wrong. The reason is that H2 is a terrible coolant. H2 is a symmetric molecule. All right? It's also got very widely spaced energy levels because it's a light molecule. And both of these features make it awful at cooling. H2 is utterly irrelevant for cooling. Instead, the reason H2 correlates with star formation is the following. Both H2 abundance and temperature are sensitive to the same thing, which is how many FUV photons are flying around. All right? The same photons that are responsible for dissociating the H2 are also responsible for heating the ISM via the grain photoelectric effect. To form an H2-dominated phase, I have to attenuate the FUV field, but I also attenuate the FUV field, I'll also get cold gas. And the temperature does matter for star formation because it affects the gene's mass. So that's illustrated here. Here's just, on the x-axis is extinction in magnitudes, AV. And on the y-axis is volume density. And the color is showing you the Bonner-Ebert mass. using the equilibrium temperature at that density and extinction. All right, so I know the density. I can calculate the equilibrium temperature because I know the extinction, I know the line cooling and heating rates. So I can calculate the temperature and density I've got at Bonner-Ebert mass. And what you see is that at low extinction, low AV and low density, my Bonner-Ebert mass is huge. It's like several thousand solar masses. No wonder I don't get any stars. All right, a one solar mass cloud couldn't collapse. It would be way too hot. It would be supported by thermal pressure. To get stars, I need to go up here, where the Bonner-Ebert mass drops down to closer to one solar mass. All right, but I can also then ask, well, what's the chemical state of the gas on this diagram? These black lines are showing contours of H2 fraction. 10% H2, 50% H2, 90% H2. They line up almost perfectly with the contours of Bonner-Ebert mass. All right, and that's not an accident. It's because the same photons are responsible for both heating the gas and dissociating the H2. So this is why star formation follows H2. It's not because H2 causes star formation. It's because H2 and star formation are both tracing where the gas is cold enough to undergo collapse. All right, and here's a similar result from Simon Glover and Paul Clark. Paul will be here starting actually tomorrow, where they did this numerically. So this is all dumb analytic models. This is, highly sophisticated numerical stuff. All right, but they get the same basic answer. If they put in no dust shielding, so they just have a turbulent cloud, they calculate its temperature and density by solving the equations of radiation or the equations of hydrodynamics with cooling, and they look at just what's the distribution of the gas in density and temperature. And they do it with a bunch of different chemistry modules. They first try no dust shielding. So assuming the FUV radiation field is unattenuated, and what you get is all the gas is warm and none of it is at high density. It doesn't form any stars. On the other hand, if you turn on dust shielding, regardless of what you do with the chemistry, you can turn off H2 formation entirely. You can allow H2 to form but not CO. Or you can allow both H2 and CO to form. What's important is the dust shielding. It's the dust shielding that lets you get this tail of gas running away to high density, at which point it collapses to form stars. So the key point is the dust shielding. That's why star formation correlates with H2. And you can actually then understand on large scales in galaxies why you get this break at 10 solar masses per square parsec. It's where you've got enough shielding that you can form this cold star forming phase. All right, and I will end there. All right. Any questions? Yes?
What is the dominant channel for H2 formation?
Turns out the dominant channel is actually catalysis on the surfaces of dust grains. For the same reason that H2 is terrible at radiating, it's terrible at forming in the gas phase. Right, the basic reason is, right, in order to form a molecule, I need to lose energy. I need to have it carried off by something. Right, in the case of H2, I need to get rid of 4.5 eV of energy. In the gas phase, where I have these two hydrogen atoms, they collide. It's symmetric. It's very hard for them to lose that energy via radiation, so they tend to just bounce off one another. On the other hand, if they're both on the surface of a dust grain, instead of having that 4.5 eV go into a photon, I can dump it into the vibrational continuum of the dust grain. And that turns out to be much, much faster. Yes?
Sorry, I missed it. What color contours are showing what quantity?
The Bonner-Ebert mass. That's what the color bar is showing. All right, the Bonner-Ebert mass is basically the same as the Jeans mass with a slightly different coefficient in front. Yes?
How do you form stars in your code? Are you using sync particles?
Well, I mean, there's no code here. So Simon and Paul are using sync particles. This is a code with sync particles. This is a purely analytic calculation. This ran on my laptop.
So what was your conclusion that the star formation follows metallicity?
So the reason star formation follows metallicity, so I mean, that star formation is affected by metallicity. That's an observable fact. All right, that's not my conclusion. That's what you see in the sky. All right, but physically, why is that? Well, okay. So the reason I would propose, and I should be clear, not everyone would agree with this, but I think it's probably the most accepted explanation, is that ultimately, what matters is dust shielding, right? I need to attenuate the FUV radiation in order to get a cold star-forming phase. All right, if the gas is being blasted by FUV radiation, it won't be cold enough to go into gravitational collapse and form stars. All right, so I need to get rid of the FUV photons, and ultimately what does that is dust grains. All right, and so that's why metallicity matters, is because it affects how much dust I have and thus how much attenuation. So that critical 10 solar masses per square parsec is what's required to attenuate the FUV enough.
I don't understand this argument because typically the UV will maybe increase the temperature by a factor, say, 3.
No, it's a lot more than that.
From 10K, or maybe even 100K, okay?
Yes, factor of 10.
Well, but then the Jeans mass is still much smaller with respect to the mass of the cloud.
Right, but it's a factor of 30 in Jeans mass. I mean, what I can tell you is that here's a fully numerical simulation, and the thermal pressure support seems able to prevent the development of a dense phase. All right, so I mean, this is, you don't believe it, but this is what Simon and Paul get. All right, I mean, I think it's basically, I think, so one way of understanding it, all right, so here's one way I would propose thinking about it, Patrick, is that, all right, yeah, the thermal support's not going to hold up an entire million solar mass giant molecular cloud. That won't work. What it will do, all right, is that the gravitationally unstable regions that you form in a molecular cloud aren't typically a million solar masses, right? The entire cloud is in fact held up by turbulence, by galactic scale processes. The gravitationally unstable regions that form within it that are going to collapse to stars are much, much smaller than that. All right, they're not a million solar masses, they're 100 solar masses, or 10 solar masses, or 1 solar mass. So if I shift the line of where the stable mass is from 1 solar mass to 30 or 100 solar masses, I get to cut off a lot of that small-scale stuff. That small-scale stuff that would have collapsed if the temperature had been 10 Kelvin doesn't collapse if the temperature is 100 Kelvin. Yes?
How are you setting up your, what is the large-scale energy injection link? I mean, how, for the turbulence, so for the case where you have an individual molecular cloud versus galactic scale, how do you choose the large-scale injection?
Well, okay, so there, I mean, in these models, there's no choice. Turbulence is simply put in. We see there is turbulence. Now, in reality, that's a very interesting question. So let me start with the maybe easier case, which is the case where the entire ISM is one continuous molecular medium. In that case, probably what's driving the turbulence is actually ultimately gravity. The way you get a galaxy like that is you have the entire, you've either had a major merger, like an ARP-220, all right, or you've got one of these high redshift galaxies that's having cosmological infall onto it at 100 solar masses per year. All right, and simply the gravitational potential energy, getting dissipated as turbulence will drive turbulence in that case. All right, there's plenty of energy available in slamming the two galaxies that made ARP-220 together to make the gas turbulent for, the duration that we observe it for. In the case where you've got individual molecular clouds like in the Milky Way, that's an excellent question. And there are a number of models for where the turbulence comes from. So it's observed to be on very large scales. It's observed to be at the scale of the cloud. All right, so whatever mechanism is driving the turbulence must operate at that large scale. But it could be large-scale feedbacks, things like supernovae or H2 regions. All right, it could be galactic scale flows, so it could be clouds colliding with one another or getting sheared in spiral arms. It could be the accretion from which the cloud formed. That this cloud formed from a galactic scale flow, stuff falling onto it drives the turbulence. In reality, it's probably some combination of all of these. All right, but actually where the turbulence in giant molecular clouds comes from is a topic of great and vociferous dispute. Would you agree with that, Patrick?
You showed the simulation of deleterious stability, so meaning the radiation pressure is not efficient to regulate the star formation. So the point is that it's only really high energy photons that can heat the gas and regulate.
Yeah, you have to separate two different effects. One is the pressure of the photons. The other is their ability to heat the gas. All right, so what that simulation showed is that basically you can't extract a lot of momentum from the stellar radiation field, but that doesn't mean you can't heat the gas up with it. You just can't push the gas around very easily. Other questions? All right, let's go to lunch.